This is a video about geometric transformations of complex numbers, particularly when multiplying by I. So I'm going to start off by drawing my Argand diagram, and we'll do a nice easy example to start off, where z is equal to 1. And I'm going to want to progressively multiply this by I. So I'm going to start off by multiplying it by just I, 1i, and of course that just gives me a result of I. I is located at 1 on the imaginary axis. So in effect what I've done is I've rotated my position 90 degrees to get to my result when multiplying by I. Let's multiply by I again and see what we get. So this time z again is 1 and I'm multiplying by I squared, and of course I know that I squared is minus 1. So I squared times z is just minus 1. So that brings me back to the real axis again. And again, I've completed another 90-degree rotation from my previous position. And again, now we multiply by another I. So we're going to multiply I cubed by z. So I'm simply taking my previous result and multiplying it by an extra I. So I cubed z is equivalent to minus 1 times I, which is minus 1i. Again, this is located on the imaginary axis at minus 1. And multiplying by I1 last time will have the effect of bringing me back to my starting position. So that is I to the power of 4z, which again is my previous result, times I, which gives minus 1i squared. But since I squared itself is minus 1, this is just an overall result of plus 1. And this just returns me to my initial position. So each time I multiply by I create a 90-degree rotation. Multiplying by I squared results in a 180-degree rotation. Multiplying by I cubed results in a 270-degree rotation. And multiplying by I to the power of 4 results in a 360-degree rotation. And of course I could keep multiplying by I, and I'll keep rotating by 90 degrees. A couple of things there to observe. First of all, rotation is anti-clockwise, and we're fairly familiar with this from trig as well. And modulus length is preserved. You can see here in the case of my example that each of my resulting points was the same distance from the origin. So my distance from the origin was not affected, simply my rotational position. So here's the second example, just to illustrate it a little bit more. We've got a point z, which represents the complex number 3 plus 4i, and I want to multiply it by I. When I calculate this out, I get minus 4 plus 3i. I'm going to plot that on my diagram. And just note, you can see the 90-degree anti-clockwise rotation if you draw in the modulus of both of these complex numbers. So you can clearly see here the 90-degree rotation. Calculate for yourself the modulus of z and the modulus of iz. You should find that they are equal. They're the same distance from the origin. Next I'm going to multiply by I again. So multiplying iz by I means I'm really multiplying z by I squared. So I'm multiplying my last result by I. And when I simplify this, I get minus 3 minus 4i. I'm going to plot this on the on the Argand diagram again. On drawing in my modulus, I can again see that 90-degree rotation from my last position. And it's worth pointing out here that I squared, of course, is minus 1. So I can also think of I squared z as being minus 1z. And this links back into a previous video that we did on the effect of multiplying a complex number by a scalar. You can see here that multiplying by a negative has meant that my z has been translated to the far side of the origin. In effect, it's central symmetry through the origin. And of course, the modulus remains the same because I'm multiplying by 1. Again, calculate the modulus of I squared z and just see if it in fact is the same as the modulus of z and the modulus of iz. Pause the diagram here, and once you've checked your moduli, repeat the process of multiplying by I 2 more times to find the positions of I cubed z and I to the 4z. In each case, also calculate the modulus, which you would expect to be the same as the modulus of all the previous points that we've drawn.